All right, welcome to section 3.2. In section 3.2, we'll be talking about substitution. All right, our goal is to translate the chain rule, remember the chain rule from Cal 1 for derivatives, to the substitution rule for integrals. Remember how helpful this chain rule is to differentiate a function, while substitution is going to be as helpful for integrating complicated functions. All right, the derivative and the integral are closely related. In fact, every rule for derivatives gives a rule for integrals. Some useful, some less useful. All right, so what we'll do in this section is we'll translate the chain rule into substitution. In section 3.3, we're going to see that the product rule gives us integration by parts. And then quotient rule would have some implication, but in fact you don't actually need it, and it's quite complicated to use for integrals, and so we're just going to put it in the trash right here. All right, so you can get away with having just substitution and integration by parts. All right, so let's first state the substitution, and then let's do an example. Theorem 3.2.1, let g of x be a differentiable function. Take u equals g of x. Then if I have to integrate some function, apply to g of x. So g of x is inside. That should remind you of what we had for the chain rule. And I have g prime of x dx outside. Then what I can do is I can replace this integral with a simpler one. I can integrate just f of u du. All right, let's try example 3.2.1. I want to evaluate this function. Already you can see it's much more complicated than what we're used to. I'm going to use substitution with g of x equals sine of x. All right, so my u is going to be sine of x. So if g of x is sine of x, g prime of x is cos of x dx. So this part here, that's g prime. All right, so let's see. My integral is sine of x to the 1/4 cos of x dx. So this entire thing here, that's g prime of x dx, and that's g of x to the 1/4. All right, so my g of x is indeed inside a function. What I'm told to do is I'm told to replace this by the integral of the same function, so still 1/4, but applied to a new variable. So instead of g of x to the 1/4, I'm just going to have u to the 1/4. All right, but I keep in mind that u is g of x, u is sine. And then this entire thing, cos of x dx, that's going to become du. Oh, sorry, there's no dx here. All right, so that's going to become du. This integral is much easier now, so I can just evaluate it using our power rule. So 1/4 plus 1 and 1/4 plus 1 plus c. I get u to the 5/4 over 5/4 plus c. All right, this is not a valid answer for the question. The question was in terms of x. My answer should also be in terms of x. But remember, u is g of x. So wherever I see u now, I can put g of x. So it's going to be sine of x to the 5/4. Let me flip the fraction plus c. That's going to be my answer. All right, let's check. If you have an answer like this and you want to check if it makes sense, all you have to do is to make sure that this is an antiderivative for the function you started with. So I need to take the derivative here. I need to take the derivative of this function. if I take the derivative, first of all, the 4/5 is going to come out. And then I'm going to use here, this is, I can even, some of teachers would have written it this way. I can think of it as u to the 5/4. So I'm going to get 5/4 sine of x to the 5/4 minus 1. And then I have to multiply by the derivative of sine of x. So the 5/4 and the 4/5 are going to cancel, and I'm going to be left with sine of x to the 1/4 cos of x, and that's the 4th root of sine of x, cos of x. All right, so every time you use substitution like we did here, to differentiate the result, you would need to use the chain rule. All right, and then the chain rule is going to give you that extra term. That's going to give you the g prime that you have here, and that's why it's part of the du. The chain rule will take care of it. Okay, but we do get exactly the function that we were trying to integrate, and so that's perfect. All right, to apply the theorem to more complicated integrals, we'll choose u equals g of x, and then we will write, so this is more new notation, I'm going to write du is g prime of x dx. All right, that's kind of what I was saying here. This entire thing, this g prime of x dx gets replaced by du. This entire thing gets replaced by du. And so we'll write it down this way. Du equals g prime of x dx. And if you solve for d of x, you'll be able to say that it's 1 over g prime of x du. So whichever one you like, you can use. Either du is g prime of x dx, or dx is 1 over g prime of x du. We can then replace dx and rewrite the whole rest of the integral in terms of u. This looks a bit strange because I have du and dx on opposite side, but algebraically, this is compatible with the notation that g prime of x is du over dx, right? It's just that I'm taking the dx and I'm sending it to the other side. All right, let's try an example using this notation. Example 3.2.2. I want to evaluate the following integrals using substitution with the given u. So in this section, I'm going to be choosing the u for u. In the next one, I'll teach you how to pick it. So let's say we want to integrate 2x secant squared x squared dx, and I'm going to pick a substitution with u equals x squared. All right, so let's use our notation from that we learned here. So I'm going to take u equals x squared, and then I'm going to write du, take the derivative of x squared, so that's 2x, that's the g prime of x here, and then next to it I'm going to write dx. All right, so this is like writing du over dx equals x equals 2x, but I'm splitting the du and the dx. All right, so I could write it that way, or I could write the dx. I can isolate one or the other. If I do it like this, what I'm going to do is I'm going to take all of this and put it where I have dx. So I'm going to get the integral of 2x secant squared x squared, and then I get 1 over 2x du. All right, so this and this will cancel, and I get secant squared x squared du. All right, now this is a bit confusing. From this part, the variable I'm integrating against is u, but everything here is in terms of x. So the next step is to rewrite it all in terms of u. And I'm going to use the fact that u is x squared, and so whatever's inside here, that's really just my u. So secant squared of u du. All right, so my substitution is finished. I went from x as my variable to an integral that is completely in terms of u. Whenever you do that, you're going to get something simpler because instead of having x squared everywhere, I just have u, and that's much easier. So now I need the integral of secant squared. Let's go. Sorry about this. What's the integral of secant squared? My table, fantastic. Secant squared is right here. It's going to be tan x plus c because the derivative of tan is secant squared. All right, let's get back to our problem. I get tan of u plus c. All right. Once again, the answer to a question where x is the variable should be something where x is the variable. So what you do now is you take your x squared and you put it back instead of u. So I get tan of x squared plus c. And that's the answer. If you want to check, you can start with this and differentiate it and check that you get this. Notice that the 2x, that's going to be the derivative of the inside. That's going to come from the chain rule. All right, one last example in this section. Let's integrate cosine of 5x dx with u equals 5x. I don't like having 5x here. I'm not quite sure what to do with it. All the functions we had just x inside. All right, so I'm told to do a substitution. So I'm going to replace 5x with u. My new variable will be u, and it represents 5 times x. Du will be that derivative dx, or if you want, dx is 1 over 5 du. All right, so I'm going to replace dx by 1 over 5 du. I'm going to pull the 1 over 5 in front. That's just a constant. And then I need to rewrite this in terms of u. That's easy. That's where I picked my u. So u is 5x. So the inside is exactly u. And then I get du. All right. So I need to integrate cosine. I'm looking for a function whose derivative is cosine. That's exactly sine. And then I put my plus c. Let's go back to x plus c. Again, you can check. Let's check this one. We have a bit of space. So if I take the derivative of 1/5 sine of 5x, I'm going to get 1/5 cos of 5x and then derivative of 5x prime. That derivative is exactly what the constant that we had here was. So that's 5 is going to cancel with this, and I'll just get cos of 5x. Notice that the 1/5 that we have here is there to cancel with the 5 that comes out of the sign when we differentiate. So if we start with cosine of ax, to cancel out what comes, the constant that comes out, we're going to have 1 over a instead of 1 over 5. So same exact proof, except that wherever I have 5, I put a. So all of these are a's. I can do the same argument with sine. The only difference is here, instead of using sine, I'll have minus cosine. And so here I'm going to get minus 1 over a cos of a over x plus c. And if I had exponential, 1 over a exponential of ax plus c. So it's the regular integral, except that I leave the a in, and I have this 1 over a to compensate the a that comes out of the chain rule. All right, so I put this in the takeaway because we're going to use this tons and tons and tons in the section on integration by parts. So I would recommend that you learn these by heart. Let me put it in. I recommend that you learn these by heart because you'll need it so much. All right, so that's it. Thank you.